All right, everybody. Can you hear me? Try that. Yeah, thanks for reminding me to record. There is a recording from the other one. It's just the second recording. Hey, you don't just hit enter to get it to post? There you go. All right, let's start out with a question. What layer of the OSI model is the IP? Okay, well, if you can't hear me, you need to check your audio settings. So Alan, check your audio settings. You do that by going to, well, here you can go here and then go, well, here it's right there. Test speaker and microphone. Hopefully you see that. Otherwise, we're gonna open up the slides and get going after somebody answers this question for me. All right. Starting question. What layer of the OSI model are IP addresses? So remember we are looking at this. Oh, you know what? I don't have a thing of the OSI model. OSI model. Layer 3, right. So if we take a look at this 7-layer model thing, oh, come on, be good to me. Physical layer, remember we have just the physical signals like, I don't know, voltages or light pulses or radio waves. The data link layer is just concerned with who's directly attached to you mechanically. And then the network layer, we're talking about our logical end-to-end addressing. So this is where bulk of the configuration happens. And we're going to see that through IP, that's how we define our networks. So this is it. This is the most important module, or IPv6, depending on, you know, which direction you're headed. That's weird. So let's get started then. Is there any other questions I wanted to ask first? Oh yeah, here you go. Which protocol requests a MAC address for a known IP address? So we're on the same OSI model thing, and we know what the IP address is, but we don't know what this layer 2, right? So yep, that's right. It's called ARP, or Address Resolution Protocol. And I know my D there got stuck or something. What we'll do is, if we know the IP address, we'll send out a request, hey, who has this IP address? And then the person with the IP address will reply back with their MAC address, and we'll store that in a table. And the next time we need to send out a packet to that destination, we just look it up in the table and send it out. Okay, so we've connected layer 3 to layer 2, and we know that layer 1 is, for us, it's trivial. It's just the way that the signal gets physically created, which that's somebody designing the semiconductor. We're not going to be doing that. Network layer is where it's all at. And why don't we just get started with the slides? I think that's what I want to do next. So yeah, we wanted to review binary first. Okay. So remember, binary is a way that we can count inside of a computer, and the numbers look like 1, 0, 1, 1, 1, 0, something like that. And each time that we go up a number here, its placeholder value it doubles the factor of 2. So if we look at this and we do what do I want to do here? I don't know. We'll place values for each place in a binary number. 128, 64, 32. I should probably have these written down in the little text file too. 16, 8, 4, 2, and 0. So we're looking at an IP address, IPv4. It's an 8-bit octet. And I missed 16. No, I got 16. 128, 64, 32, 16. Yeah, I got it. 8420. Okay. Good. So each time we go up one place, we increase the place value by a factor of 2. So I guess we can call that, it's more appropriate rather than the 0 place to call it the 1's place. So then 1, if we have a 1 there, then we have a 1. If we have a 1, 0, then we have 2. So that value is 2. 1, 1, 0, it's 4 plus 2 plus 0, which would be 6. And then 1, 1, 1, 0, it's going to be 8 plus 4 plus 2. That's going to get you 14. 15, sorry. Nope, 14, because we needed the 1 there to make it 15. My bad. Okay. Hopefully that didn't confuse you. This is going to be, these place values are going to be important for the way that we do subnetting. We'll go over them again, but I wanted to touch on that before we kick this off. All right. I don't know. Are there any questions on how PowerPoint works? Come on. Yeah. Or how PowerPoint doesn't work? Okay. Well, as the slide says, we'll be doing IPv4 addressing. And if this comes up, then we'll be able to go through the slides. Oh boy. What? Wow. Maybe I just have too much stuff open. Let's close packet tracer. I was going to ask people if they had questions from the last packet tracer activity, but you know what? Maybe that's what's holding me up. Let's take a look. Task manager. Yeah. Something's clocking that CPU up. What is it? The hell? Okay, well, now it's better. That means I have control of my computer again? No. All right, well, let's try, come on. Managing PowerPoint. Parallel PowerPoint. Where did I put this here? Freaking hello me and PowerPoints for module 11. All right, well, that's how you use the task manager when Windows can even run its own programs. Thanks, Microsoft. Oh, I didn't, of course, I haven't set up the slideshow either because, I don't know. There you go. All right. Okay, now we're cooking, kind of. Better. Okay, so an IPv4 address, we know what they look like. They look something like this, 192.168.1.1. As an example. What exactly does that mean? So 32 bits, what that means is that there's 4 sets of 8 ones and zeros. So what an 8 ones and zeros are going to look like. That's 8 ones and zeros right there. If we do that 4 times, 4 times 8 makes 32. We write IPv4 addresses in dotted decimal format. So these numbers are the decimal numbers that we're familiar with. They're the ones that we use to count the amount of money in our bank account, or how old we are, or how many miles are on our car. We know decimal intuitively. However, when it comes to IP addresses and subnetting, what was once intuitive becomes not so intuitive. So let's take a look at how we manage these. If there's one thing that you guys take away, I want you to remember that we split the IP address into 2 portions, a network portion and a host portion. And our goal by the end of the night is to be able to adjust how many bits are in the network portion, how many bits are in the host portion. Remember, we look at these, they're decimal numbers, but the computer sees them as these binary numbers. So we'll say things like borrowing a bit, and that's going to refer to in the binary how we take one of these digits here and switch them from either the network portion or to the host portion. All right, so I don't know how many pieces are in a IPv4 or an IP address. Really, any IP address has these 2 portions. I should say how many portions? How many portions? This is critical. It's there's going to be a lot of numbers here, but really all we're looking at is functionally it functions as 2 different numbers. So yeah, there's 4 octets. Yeah, there's 32 bits, but the one number or the way that we divide these is critical to know this one little thing right here. And it should be RNN IP address. So English grammar is sliding, I guess. 2, right. There's 2 pieces. There's a network portion and a host portion. Keep that in mind for this whole time, and you won't go far wrong. And essentially, we're addressing 2 things with this one number. We're saying what group you belong to, so like your last name, Smith, And then over here, you know, Harold, your first name, so you can individually identify yourself within that group. Great. Let's see how well that works. So, okay. You'll hear the term anding. All that means is that it's a process for splitting the IP address into the two portions. That's it. So we already know that IP addresses are two numbers hidden inside of 32 bits, hidden inside of 4 decimal numbers, but there's just two numbers here, a network number and a host number. And we decide how many bits are in the network portion and how many numbers are in the, or bits are in the host portion using this thing called a subnet mask. And the anding process works by screening out bits so we can define the network number. What we're looking at here are two ways to define which part belongs to the network number and which part belongs to the host number. So another dichotomy. All right, let's start out. We'll make sure we've gotten the first part down. So what are the two numbers, or the two portions in an IP address? Now, you can't look at it. One of the answers is on the slide. Network and host, right. So there's an IPv4, there's two ways that are alternates to each other in order to be able to tell which part's the network and which part's the host. The subnet mask, the subnet mask and the prefix length. Both of these do the exact same thing. And you won't see them together. You'll either see one, but this is the new way to do it, and it's easier to use. We'll talk about that first. And this is the old way to do it, which it matches the way that we do the dotted decimal with the IP address, but otherwise it's much less intuitive. All right, so with the prefix length, we're saying these are the number of bits in the network address. So if I write a /8, there are 8 bits in the network address, like that. /8, 8 bits. What if I have a /16? How many bits in the network portion? Oh, somebody's jumping the gun. There you go. Oh, wait, oh my God. There you go. All right, guys, I have my messages have somehow they switched private. There we go. So I've been asking questions on the chat too. It's fine. You can hear me, you're participating anyways. All right, so the slash notation, sometimes called CIDR notation, is the new way of doing this. This is the way we'll do it in IPv6. But these subnet masks do the same thing, and that's how you're going to configure IPv4 addresses. So yeah, no getting around it. You have to learn these. And the way it works is the same way as with dotted decimals. So each octet goes from 0 to 255. So how many numbers in 0 to 255? There's a question mark. So how many numbers are there between 0 and 255, inclusive, I guess? $256, exactly, yes. Because we start at 0, 0 counts as 1. And if you add 1 plus 255, you get 256. All right, so each one of these octets can count 256 digits. When you get to 256, however, that's the next bit up. That's a 9, it'd be a 9th bit. We go to the next octet. And subnet masks doesn't quite work like that, though. Subnet masks always fill in from the left to the right with ones. And so there's only certain numbers that'll show up in decimal. So recall, let's go here. We have the place values, 128, 64, 32, 16, 8, 4, 2, 1. And what those are the binary place values. And these will be important because we'll use those in order to be able to do subnetting. So if these are maybe we'll put one more row in. Separate it from our box. I'm not sure if that's going to work. Let's see, Control C. All right, so binary placeholder values. So if we're filling them in from the left for a subnet mask, let's go back to that slide deck. We're filling them in from the left. If we look here, we're filling up complete octets, and that's the easiest way to subnet. So each time we just fill an entire octet up with ones, and entire octet of ones is 255. We'll find that this way of subnetting is very intuitive, and that's the way it was originally conceived. But then the whole world got on board the internet, and people had to be more, I'm going to say, sparing with their use of IP addresses. And so we came up with subnetting as a way to extend IPv4's life, which so far has been indefinite. Okay, that's ending. We'll get to that in just a second. So if we're filling in these place values from the left, see there's only certain values that you get. So 128 is if you're 1 bit inside of that octet is belongs to the network. So if we look at the slide again, right here, you can see in this last octet, one of the bits is part of the network address, and our subnet mask has a 128. If we take one more bit, you can see here, we add 64 to that. And if we do 128 plus 64, we get 192. In fact, we could turn this into a calculator, subnet calculator. But let's not do that. All right. Hopefully you get how that works. If you don't get it right away, don't worry about it. For today, we're going to stick to the prefix length notation, but you definitely need to know this. Normally, if we're doing this in person, I'd hand out one of these. Come here. So here's the home page. You go to PowerPoints, Yeah, kind of misleading. There's more than just PowerPoints in here, but not a lot more. There's a handout for subnetting. And since you're not here in person, I would print this out and hand them to you. But you can see here that the subnet mask numbers are listed out for you. So if you forget what the number is, eventually these numbers will just be kind of second nature. But if you forget, you can look at this table and say, oh, if I'm borrowing 3 bits, the subnet mask is 224. So you can do it the same way. If you start out with /24, end up with /27, that's 1, 2, 3 bits. This actually gives you the subnet mask to CIDR notation as well. So remember, these are just remember right now, the subnet mask and the CIDR notation, they're the same thing. So using both together would be redundant. Okay. All right. So what does the prefix length determine in an IP address? All right, so what does the prefix length determine in an IP address? So we already know that there's 2 numbers or 2 portions in an IP address. We determine, right, how many bits are in the network portion using the prefix length. And then whatever is left over, whatever is left is the host portion. So this guy's barely got any hosts at all. In fact, you can count them really easily. There's 2 binary bits. You have 4 possible numbers, and we know we will find out that the first and the last one aren't usable, and so that only gives us 2 usable IP addresses, the minimum size network that we can have. All right, so here's just, don't sweat the ANDing thing. This isn't gonna happen, at least this isn't the way I'm gonna teach you guys. But if you have a subnet mask here, and you have a host address here, you just write the bits of the subnet mask and AND them with the IP address, and that gets you the network address. So basically what it does is it copies all the bits that have 1s, and it masks out or turns into 0s all the ones that don't. And that gets us a network address, which will be important when we start configuring routes. All right, but for right now, we have 2 portions, a network and a host address. And I don't know. Wait. All right, so within those 2 portions, so right now we're looking at just the host portion. And maybe I should edit this so it just said host addresses. The host portion can be a unique host address. So, you know, that first name. Or it can be one of these special addresses. This network address is the first address in the range of host addresses. So if we got this example right here, we have a /24. The case where the entire host portion is 0, That's the network address. Remember when we're ANDing up here to determine the network address, you AND zeros with anything and you get a bunch of zeros. So that's the first special address. We can't use the network address. It's special. It defines the network. There's a bunch of host addresses. We just have one. It just says one host addresses, but everything else is going to be a host address. So in this case, we've got a broadcast down here. We've got a network up here, and then we've got, I don't know, 254 host addresses from 1 to 254. And this last address is a broadcast address. It goes out to all the people on the network. They all pick it up. And we'll find out there's protocols like DNS and, not DNS, DHCP and ARP, where broadcasts are important. You broadcast the entire network just to get a response from one. All right, so there's 3 types of host addresses. Which host address is all zeros? What's the all zero host address? Someone's gonna have to answer because it's kind of an important thing. Right, the network address. So right here is the network address. If it's all zeros in the host portion, then that's a special address that defines the network. We can't use that to address an endpoint because it defines our network. So it's used for routing. All right. Good. We're going to call that a win, mostly because we've got a lot to do. IPv4 unicast, broadcast, and multicast. So now we're looking at the network portion. And there's 3 types of network portion as well. Yay. All right, so we split the IP address into 2. We found out that there's 3 host address types. And there's also 3 network address types. Symmetrical, but very different. So yeah, broadcast is in there twice, so that's not confusing. Unicast, which is up here, is just 1-to-1. So the uni, think about that like a unicycle. Univision, not really sure. I mean, it's still the same prefix, but like, now that I'm thinking about it, like one vision, like that sounds kind of conspiratorial. Unicast means from one device to the other, and this is mostly what we'll be doing. So we're going to configure a unicast IP address so that we can uniquely identify our endpoint over at least our internal network. And then I'll get sent to a unique destination. In this case, a printer. So we can print out our airline tickets and, you know, fly off to some exotic destination. And the examples they give you are 2, we'll find out our private IP addresses, 172.16.4.1 and 172.16.4.53. Now notice they don't give you a subnet mask with this. It's yeah, in this case you need to, because they're not using the classful address. We haven't even talked about what classful means yet. So forget I said that. Broadcast. All right, so broadcast Broadcast is, well, 1 to everyone. Imagine just standing up on a table and yelling out in the middle of the room, hey, everybody, do you want to see the mole on my nose? And everyone's going to be listening. And they probably aren't going to invite you in any parties, but you'll get all their attention, at least for that moment. That's what a broadcast is. If you don't know who to talk to or who to send the message to, you broadcast it. And there's some protocols that work like that. We already talked about ARP, and DHCP is one that we haven't talked about. They both send out broadcasts to start out. So they're like, hey, everybody, do you have this IP address? Anybody? Anybody? And then they wait for a response from one person. So there you go. One to many. Multicast is the next one. And we're not going to do much with this, but know that there's a special network address so that you can send one packet to a group, a select group. And we won't talk about why that's used, but it's important too. All right. So there's 3 types of network address. Which network address type is 1 to 1? If I was slick, I'd have you guys use like Pear Deck, and we'd all do this in real time in the slides, but yeah, that's work. It's easier to set it up in chat. All right, RFC 1918 is the way that we get private addresses. So your head's spinning from numbers. Let's just take it back. There's network addresses and host addresses. This is a special type of network besides the 3 that we talked about. So within all the possible network addresses, we've set aside 3 groups of numbers so that people can use them in their local networks. We'll find out why this is important. It's a very important aspect of extending the life of IPv4. Essentially, we're saying we won't route these addresses across the internet, so you can use them in your network, your private network, and not worry about stealing somebody else's unique identity. So, which happens sometimes. There's plenty of bad actors on the internet, or just incompetent actors. So these ranges right here, these special ranges, 10.0.0.0, it's an entire class A that you can use inside of your private network. 172.16.0.0 and /12. So there's like 16 of these class B networks. We'll find out what a class B means. 192.168.0.0/16. This is 256 class C networks, because the network part is right here. The entire octet belongs to the network. All right. So when you get a public IP address, somebody assigns it to you. So either, well, in this case, they're all handed out. So it's going to be some service provider that's going to give it to you, or your company already has a block. So the only ways to get them anymore. NAT. So if we've got these addresses that you can't route across the internet, of course, everybody wants to get to the internet. You have to translate your private address to a public address, and we do that through NAT. We're not going to talk much about NAT. Just know that that's how we make private IP addresses usable. Done. I'm going to ask you a question about it. Special use IPv4 addresses. So there's lots of ranges that we just can't use to address endpoints. And some of them tell us about whether or not the network's functioning. So the loopback address is fantastic. And sometimes it's really, I don't know, 127.0, it's a whole entire class A for some unknown reason. They probably didn't even know at the time when they were making it up. They're like, we've got so many of these numbers, like we can't possibly run out of them, you know, within our little project. So let's just give entire class A to loopback addresses. So if I ping the loopback address, I can go here, command prompt, and I can go like, you know, ping 127.0.0.1. And all that's doing is it's pinging my interface to see if my TCP/IP stack is working. So loopback addresses, we'll use them, I don't know, maybe not in this class, but you can also use them to make like fake networks in order to populate a routing table when you're learning how to configure routing. We also use them for routing protocols sometimes as a router ID. So yeah, I mean, are you going to use an entire class A of loopback addresses? No, it's almost inconceivable. But you definitely, you can, there's situations where it might be useful to use more than one. So link local addresses. We'll find out that these are mandatory in IPv6. In IPv4, if you see an address like this, so you go to, let's go back to the command window. Whoa. Okay, not working very well. Let's see the command window here. And we go, I don't know, ipconfig. Here is my IP4 address. If instead of seeing 10.0.50.37, which means my DHCP is working, and I see, you know, that 169.254 something something, if it starts 169.254, then I know that my computer is not talking to the DHCP server, and there's a problem. So mostly when we see this, it's a problem. Link local addresses in IPv4 means something's wrong. The idea would be that, you know, if you don't know anything about networking, the computer can configure itself without a DHCP server, and you can route things locally on your network. So if, you know, you've got like a media server and you've got a whole bunch of movies on it on your local home network, and everybody's using those APIPA addresses or the link local addresses, and they could talk to each other still. They just can't get to the internet, but yeah, everything's on the internet now. So if you see that, panic. Something's wrong. All right. Back in the day, we split things up in classes. Just know that colloquially, class A means anything that has the first octet belongs to the network. Class B for us now in modern days means that the first 2 octets belong to the network. Class C means the first 3 octets belong to the network. And class D and E means go home. You can't use those ranges. So anything that's higher than 223. So if we have an address that's, I don't know, 233 dot 50.50.5. That's in a range that you can't use for addressing unicast destinations. So maybe some application uses 233 as a multicast address, but I wouldn't know what it is. Just know that if the value of that first octet is greater than 223, yeah, you can't use that address. Go fish. So what we're going to be talking about are classless addressing, and just bother with that term. It just means that in order to define the network address portion, we need a subnet mask. So the IP address and the subnet mask always have to go together now. That's it. That's all it means. And that's what we're going to learn. So just know that's the way it always is now. So this is where you used to get numbers from when they had them. Pretty sure they've given them all out to ISPs or companies. So I'm pretty sure the organizations still exist. I don't know what they do. I mean, obviously they have to keep track of who's got what, but it's, and they probably hand out the IPv6 addresses still. All right, broadcast domains. I skipped this. Anyways, a router defines a broadcast domain. So what that means is that if you send out a broadcast, remember that special IP address that goes to all destinations, as soon as it gets to the router kindly looks at it and doesn't forward it on. So it's a router stops broadcasts. So the broadcast, this is, as far as the broadcast is concerned, this is all it can see. Everything that's in that box. Anything else, if there's like 500 million connections off of this router, which would be a very impressive router, world record breaking even, then it doesn't see it. The broadcast didn't go anywhere past this routed interface. All right, and that's a synonym for that is that it segments a network, and then you can put filters, so you can filter packets at the router. So there's a lot that goes on at that routed interface, besides just, you know, the stated purpose of the router, which is to send a packet to its destination. So if you're, so fortunately ARP is only concerned with devices in your broadcast domain or within your same network. DHCP, however, sometimes there's a DHCP server that you're using that's not on your network. And so there's a special way that we have to be able to sneak those particular ones through to the DHCP server. But also not talking about that today. Got so much. My gosh, it's already been 50 minutes. All right, we'll take a break at the hour because it's going to be fun-filled. All right, so now, how do we split up between the network portion and the host portion? Oh, that's a fantastic question. I'm glad that I asked it to everybody. What are the things that define the network portion of an IP address? The things. Here, it's on the slide. And I want both of them because I said things, it's plural. So there's two different ways to do the same thing, which is define the network portion. We have to go back to what, the network portion is. All right, the prefix number. It's right here, the prefix length. What's the other way of doing it? No. So we will never configure binary. We use it to illustrate the effect of a subnet mask because it's more granular and it's how the computer thinks. So one of them is the prefix. Is one way. To define the network portion of an IP address. And that's the way we'll use, that's what we'll use in an IPv6. So you can see here, /8, that's the prefix. We call it a prefix because it starts at the beginning and goes backwards. So it's necessarily from the most significant bit, starts with the most significant bit. So this is one way of defining how many bits we have in the network portion. In this case, we're saying that there's 8 bits in the network portion. And we can count them right here because we've conveniently put it out here in binary. So we can see that there's 1, 2, 3, 4, 5, 6, 7, 8 ones. And all the letters up here mean is that and that means all that is network portion, and all those that's all host portion. And they did it in bold too for the network portion. Makes sense. So what's the other way? Other way to define the network portion of an IP address. It's going to be a long night, guys. It's the other way to define the network portion of an IP address. We have a prefix length. This one gives us 8 bits. This one gives us 16. Right. So the subnet mask right here does the same thing as this prefix length, but in a way more complicated way, unless, like it says here, we're subnetting on octet boundary. So you have all the bits, the subnet mask are 1, you get 255. There you go. So all the bits in that octet belong to that, to the network. And all the bits in these 2 octets belong to the network, it's /16. And all these bits in these 3 octets belong to the network. You can see 255 to 255 to 255, which is going to be a really common net mask. In fact, we'll say default. And you know, they're all factors of 8, right? So this is 8, this is 8 times 2, this is 8 times 3, because we have 1 octet, 2 octets, and then 3 octets. And hopefully that makes sense. Because it's not getting any easier than this. This is it. pretty soon we're going to start splitting them down the middle of the octet, and the decimal numbers are going to get weird, and these prefix lengths are going to be like odd numbered, all so that we conserve IPv4 addresses, because no one seems to want to make the transition to IPv6 completely, unless you're Comcast and you've got some vision of the future. Okay, or Google, it's a relatively new company. Okay. All right, so 2 different ways to do the same thing, but essentially what we're doing is we're splitting up the IP address into the 2 portions. One portion is the network, and then the other portion is the host. Host. So we identify what group we're in the world, really, and we identify which member we are of that group. Okay, well, that makes sense. Otherwise, the rest of this is going to be really, really confusing. Okay, so we're subnetting on the octet boundary. Super easy. So we've defined this network right here, 10.0. If we want the next network up, guess what? We just add 1, decimal add 1. And that's the next network. So this group, 10.0, is separate from this group, 10.1. Unless there's a router between them, they can't communicate. So we've talked about there being 2 portions. Now we're focusing on just that one portion, the network portion. And what does it do? It defines network. You've set up a tribe. You've said, this network, these guys all belong together. Anybody that starts off with 10.0, they all belong together. If you don't have that 10.0 in the front, we don't want to talk to you. We'll talk to you through a router, but we're not talking directly to you. You're not part of our network. So when it's on an octet boundary, it's very simple. You want to go to the next group, or you want to create a new group, you just add 1. Next one, all the way up until 255. And once you get 255, that's your last group. You see that we've got 256 of them, 256 groups. And each group has a whole bunch of hosts in it. So these are pretty big tribes. If we take this /16 and we move one of those octets from the host portion into the network portion, now we've got a /24. And you can see the way we count is a little different. We'll go all the way up to 255. And then once you get to 255, the next network up is 10.1. And maybe, I guess maybe now is a good time to look at how that works. Because this is how you get more than 254 hosts or more than 256 networks. You pull in bits from the next octet up. In this case, we pulled in the entire octet, all 8 bits, and we're going up. So when we get to 255 on these .0 guys, we go up to the next one. It's the same group. It's the same. Oh, I'm sorry. No, each one of these is a different group. Not bad. But we've got way more groups here because there's way more bits in the network portion. Okay. So they go from 10.0 to 255. The next one up, you add 1 to 255, it's 256. That's too high. That's the next bit up. So you raise the next bit by 1, and then drop the rest of the bits down to 0. So let's try. Try doing that. Let's try doing it this. So, so what's the next host address after 10.1.2.255/16? So now we've gone we're all the way up to this one, 10.1.2, and oh, sorry, this is a host address, and it's /16. It's over here. So it's a 10.1. We're in this group right here. All right, we're talking host addresses now instead of network addresses. Okay, I didn't mean to switch on that. So now we're looking at the other part, the grayed out part. And yeah, so within this 10.1 area, if we go up to the next host after 10.1.2.255, yeah, you get 10.1.3.0. And that's, yeah. So I switched to the host portion on you guys. That's, I don't know, maybe a step too far for some of you, but I've got a whole book of these things that you guys can go through and do so that hopefully eventually it makes sense to you. All right, so we're at the hour mark. Let's just finish out this subnetting within an octet boundary, and then we'll take a break. Oh, well, and we've already gone outside of that boundary, so I don't know why it says subnet within an octet boundary at the top. That's a little bad. This is how things get weird. Now we're taking that /24 and we're borrowing bits from within the octet. Sure, every time we borrow a bit, it doubles the number of subnets. But now we've got this weird number of hosts, not 256. Or number of addresses. We'll refer to the number of possible addresses, which will include the broadcast and the network address, because it works out as a factor of 2 that way. So we can start borrowing bits in the middle of the octet, and now the subnet masks get kind of weird. But this is really, for us, this is an all-inclusive subnet mask set. At least these octet numbers. Remember, if we look back here, and no, from here, then we also get to see those numbers, plus a couple that we won't use, at least not for subnetting. Okay. All right. So we want to conserve IP addresses, so we're adjusting how big the network portion is. And since everything that's left over is the host portion, we're also adjusting the size of the host portion. And this is where we're going to pick up just a bit. This is take 5. You guys can ask any questions you want as well. Pause. Okay, so we're back. Before I forget, let's cover some of this. So I've gone in and I've put in some of your grades. So you can get on here. I think you can see your grades. If this doesn't show up. So Yeah. Labs I'm less worried about than the exams. A lot of you are way behind on the exams, so yeah. Where are the exams? There we go. So I put in some default grades. Oh, for the exams, you can see that some of you haven't been doing them. Try and keep up. These exams are actually fairly challenging because they include a bunch of modules all in one. So yeah, they're not due, but and when you take the exams, that default grade will get replaced. But should give you an idea of where you're at. Okay. And just to make sure, I'm going to enable the grade section in case that's something that you guys need to do. All right, so grades. Second to the last. All right, so you can look at your grades. That matters to you. Also, these slides are on. Are they? Are they though? No. I don't know. I don't think I've updated 1, 4, 3, 5, 6, 9, 10. All right, so I need to upload 11. This one, but all the other slide decks are on there if you want to look at those. All right, it says PowerPoint slides, and then also the Subnetting workbook that we'll get to momentarily. That's also there. Okay. So back to the slides. We're talking about subnetting. If we subnet on the boundary, it's pretty straightforward. There's only 3 numbers. 3 possible numbers for prefix lengths and 3 possible subnet masks. What we'll find is that this is typically the way people will drive things, but when you're talking about public IP addresses, you have to get very stingy. And so, yeah, subnetting on the octet boundary just stops being an option, and you end up with this. Okay. So it ends up this number back here is going to be really important for us when we're doing subnetting because we're not going to convert from binary to decimal. Just it's not practical. The number of addresses per subnet will be how we'll calculate what the network addresses are. It'll also be determined. It'll also be the way that we determine from the network address what the possible host addresses are for that network address. So this last column ends up being critical for us. So recall that we have positional notation for binary. And all it is it's 1, and then we double that times 2. Double that makes 4. Double that makes 8. Double that makes 16. Double that makes 32. Double that makes 64. Double that makes 128. And that's 8 bits. Okay. So we're figuring out how to get to the next network. We'll use these positional notation numbers. All right, let's see what else is in store here. All right. Oof. All right. We'll just skipping /24, I guess, because it would be too easy. All right, let's hold on the slides then. All right. So how do we subnet? Let's start out with the network. How about that? 182.168.1.0, and it's got a prefix of /24. Remember, prefixes are the new way to do it. We'll be using those for simplicity's sake. All right. So if you have a /24 prefix is how many bits in the network portion. I can't be bothered to go back and correct the spelling of the portion. 24, right. So that's what makes that such a great notation. It's a /24. That means that these first 24 bits, or the first 3 octets, belong to the network. All right. So we're going to take this last octet and we're going to subnet it. What does that mean? Well, we can visualize the number of numbers that are in that last part right there. So if we write down just the first part here, you know what? 192.168.1. We're going to take that whole last octet. We're going to visualize it as a range of numbers, starting from 0, and going all the way to 255. So every number in between is in here. This is the entire range of numbers. You can think of it as like, I don't know, a pie or a cake or a pizza, but we're going to cut it up. All right. And so what does this look like? If we're visualizing the numbers using this box method, we write in side of the box the entire range of numbers from 0 to 255. Or all 256 possible numbers for that octet. All right, and we want to create another network. So we borrow a bit, and see we go from a /24 to a /25, and that gets us 2 networks that are half the size. So every time we borrow a bit, cut the network in half. And we can visualize that by just taking this box and writing a line down it. What if we want to borrow another bit? Well, as long as we apply it to every single one of the networks, just draw another line straight across there, split both of these in half. Now, each one of these is /26. We've gone from having 2 subnets to having 4. So if we went from 2 to 4, if we borrow another bit, how many networks will we have? All right, we borrow one more bit. Now then, how many networks do we have? 8, right. We split both of these in half. And now, or maybe we split them both in half this way. It's fairly trivial. Well, not now that we have the numbers there. But now, we've got 8 networks. And since we know from that positional notation, so we've borrowed 3 bits. We borrowed 1, got that. We borrowed another one, we got that. Borrowed another one. We know now that there's 32 hosts in each network. So if we start, wait, up here with our network address, which that goes to network address, just the octet. All right. So if it was 192.168.1, we know that the first range of hosts is going to be from 0 to 31. But if we add 32 to 0, we get to the next network. If we add 32 to there, we get to the next network. If we add another 32, we get to 96. If we add 32 to 96, we get 128. If we add 32 to 128, we get 160. If we add 32 to that, we get 182. If we add 32 to that, we get 224. So we can find the next network. We don't need to use digital to binary. We just need to know how many hosts or how many possible addresses are in each network. And we can very easily determine that by writing down the positional notation and then figuring out where the subnet mask stops. And where it stops at, that's the number of hosts per network. All right, let's try this. I borrow one more bit. So I was at 32. Now how many host addresses per network? With, we'll call a /28. Or we're borrowing 4 bits. How many hosts per network? Don't forget, look at the positional notation. Look at this number down here. I know it's a lot of numbers. $16. Right. So we look at the positional notation where the borrowed bits stop. That position tells us how many hosts are in the network. And why is that important? Because we need to know what the next network number is. And if we know what network number we start with, which adds 16 until we get to the final network, or one past it, which would mean, we get 255, then that's all the network addresses. And that's what we need to know to be able to configure the hosts and to do routing. All right, so let's take a step back for a moment. So this box notation, it's a neat way to visualize, and that's the way that we'll do subnetting. Oh, I didn't resize this at all. Hell no. Okay, it was weird. Okay. Now, let me go, all that, just do this. All the way back up to here. All right, so remember, we're going back to this again. An IP address has 2 parts, network and a host. So if I give you a, I don't know, 33.0.0.0/8, which number is the network portion? So we're going to split this into network and host. Remember, it's 2 numbers. Which number or numbers is the network portion? And if we go to the cheat sheet, no, cheat sheet. Oh, well. All right, that's a good guess. 33.0.0. Almost always, we will almost always start with the /2024. So mostly, yes, but not now. So /8 means that it's the first 8 bits belong to the network portion. Each dotted decimal represents 8 bits. So we're looking at /8, looks like this. There's our subnet mask. Remember, these are the same thing. Got a crap load of hosts. Which number is the network number? Yeah, just 33. Just the first 8 bits, or that first part, and we can see here that it's just that simple. Okay, let's go into one more. Where am I doing that again? There you go. Got a lot of different things open. All right. So 192.157.77.56, and it's a /24. What is the network part? Or the network number. And /24 is going to be kind of a go-to number. Right. So those first 3 octets belong to the network. Exactly. Normally I'd give you guys a sheet of this stuff, but it's already been an hour and a half. I'm not going to drive you guys longer than a couple hours, so we're going to skip doing more of those, since they seem to have the idea that we're defining a network using the subnet mask. Let's take one of these. So instead of the CIDR notation, let's use this. Is that copyable? This one. All right. Network portion. Which one? What's the network portion of that? Right, the first 3. 186.13.23. What's the host? We'll almost never use the host by itself. So normally, if you're going to say the host address, you would add the network address in front of it, because, like, instead of saying, oh, John, it would say John Smith, right? And he's part of the Smith family. Then doesn't mean a lot to say, hey, go talk to John. John's a very common name, even in the Bay Area. And doesn't help us identify him. Okay, let's try this one here. All right, network. Go. Ah, even quicker back type network. Good. So see the net mask. We know the 255. 255 means the entire octet belongs to the network. So we've just chosen that. And that octet, the rest of them belong to the host. So normally when we write a network address, we're going to write it 28.212.0.0. We add the zeros in there to make it easier to identify as an IP address. Just know the zeros, they're placeholders in a network address. Unless they're part of the subnet mask. So if that was the number that we were given and we had the same, not same subnet mask, but the subnet mask instead was 255.255.255.0, then what is the network? So we changed the IP and we also changed the subnet mask. So now it's a totally different one. Divorce yourself from the last one. Almost. So in this case, remember, computers don't distinguish really. 0, just another number for a computer. So 28, for us, it's like this crazy concept of nothing. But computers start counting at 0, and so 28.212.0 is going to be the network, because the first 3 octets belong to the network number. But yeah, Alan wrote it correctly. That's how you would write it still. But you definitely have to have the subnet mask along with it, just so people know that it's the first 3 octets. All right, so we got the concept that we're splitting these things up into two portions. Okay. All right. So we start out here with the /24, and a colloquial way of saying /24 is class 3, class C, ooh, which means a /24. But we need to make, we need 14 subnets. So we can do this in a number of ways. But we're going to use this graphical thing right here. So it was 192.10.10. So write in our network address. So there's our network address. And it's 192.10.10. And then we're going to explode that last octet into this right here. So that last octet goes from 0 to 255. We need 14 count them, subnets. So we're going to split this in half. I've got from 0 to 127, and from 128 to 255. So we split the range in half, taken the cake, cut it in half. But it's only given us 2 subnets. So we borrowed one bit right there. We've gone from a /24 to a /25, so we're at a /25 right now. See, let me write that. Good. Doesn't think it's an operation. So we've borrowed 1 bit, taken this thing up to a /25. But we only got 2 subnets. We need to get a couple more. So we're going to split this in half again. All right. So now, borrow another bit, onto a /26. And instead of having 128 in each one, we've got 64. So to get to the next network, take 0 plus 64. To get the next network, we get 64 plus 128. 192. Yeah. Okay. All right. But it says we need 14. Seems like we're a long ways away, but really we're only a couple cuts away. We've got 4 subnets. We've doubled the number of subnets we had to 2. We doubled it again to 4. We're going to double it one more time. Double or nothing. All right, now it's going to get basically less and less creative color-wise, but it's fine. Super uncreative. Right. So much so that I'm going to take that, change its color to. Okay, good enough. All right. So we go from, so before we had 64 in each one. Now we've got 32 in each one. So we go from 0 to 32. 32 plus 32, 64. 32 plus 64 is 96. 32 plus 128 is 160. And 32 plus 192 is 224. So let's just, is there a quick way left to line these? Yeah, looks a little bit better that way. Okay. All right, so we borrowed 3 bits. So how many subnets are there? Count the colored squares if you like. 8. Right. 1, 2, 3, 4, 5, 6, 7, 8. So the great thing about using these squares is that we can very easily visualize what our subnets are. And in order to get the network addresses, we're just going to take this and tack on this last octet. We'll write them out here. We'll write out all 16 in a minute here. But in the meantime, I'm trying to decide which way I want to cut these. Let's do it this way, and we'll just make them all same color. How about that? Light blue. It's not super creative. It's not super high contrast, but just because they're the same color doesn't mean that they're related. We're just we're creating a boundary, and that one's just too close in color to really be distinguishable, so we'll do it that way. All right, so now each one of these guys, we borrowed another bit, are 16, got a slash 27. And 0 plus 16 makes 16. 16 plus 32 makes 48. 48 plus 16, 64. 64 plus 16, 80. 80 plus 16, 96. Plus 16 is 122, is that right? 2, There, what's this? 112. Ugh. All right. And then plus 16 is 128. Then plus 16 is 224. Wait. No. $144. Thanks. Plus 16 is 160. Plus 16 is 176. Plus 16 is 208. Some of these ones are just the ones that are a little bit weirder. I'm having more difficulty with. But ultimately, we started out with one subnet. We borrowed, oh wait, we borrowed 4. So now this is /28. Borrowed 4 bits. And we created 16 subnets. We were needing 14. We'll find that if it's not right on a factor of 2, then we're going to go over the amount that we need, which is fine. That's just how the math is going to work out. All right. So that's how you subnet using these boxes. And we're not going to do a whole bunch of examples of this. And I think we're going to have to put some of this stuff off because more than 2 hours is just, I don't know, that's my limit. So I like this book. And so let's give you guys a couple out of here. So do, this is too big. Something reasonable here. There you go. Oh, still doing it classfully. All right. Let's probably could have picked a couple of these out in the first place, but this one's good. Okay. Which is basically the same thing we did. Almost exactly. Okay. All right. Problem 3. They still have you go by address class on here though. So it's class C. So /24 is the subnet mask. All right, I'll assign you guys a problem out of the book then. But you can still do this one. I'll put it in there. I'll post that one up for you guys, and let's take a look at this really quick, and then we'll call it a night. So what we're looking at was if we're starting out at /24, how do we subnet? Yeah, you need to be able to identify networks. Or else a routing table is not going to make sense to you. And the best way to be able to identify networks is to understand subnetting. So yeah, most of the time the networks will already be set up for you, but if the numbers don't make sense to you, then the routing table is going to look like a mess. All right. So remember we were talking about how to count in dotted decimal. We get up here to 255. We start borrowing bits from the next octet. This is basically from here down is what we've been looking at. But you can also borrow bits from the third and the second octets. And that's what this looks like. And what it does, the number of possible addresses, is it increases them, into the thousands. So now, if you've got this entire octet belonging to the host portion, and then you borrow another bit, you're doubling that amount. So it's 2 times that 256 number. You get 512 possible addresses. There's 2 of them you can't use, but and then every single time you double that number again. All right, so if we want to make 100 subnets from this private IP address, how do we do that? And let's see how to do that. So we borrow 1 bit, that gets us 2 subnets. We borrow another bit, we get double that to 4. We borrow 3 bits, we double that to get to 8. We borrow another bit, get that to 16. We borrow a 5th bit, 32, double 16. Borrow a 6th bit, double that, 64. 64 is almost there, but it's not enough. We have to double it again. So we need to borrow 7 bits to get 100 subnets. All right, your turn. So to satisfy the requirement for 100 subnets, we have to borrow 7 bits, or 2 to the 7th tells us how many subnets total we've got if we borrow 7 bits. Okay, your turn. Create 1,000 subnets, starting with this big class A. How many bits do we have to borrow? Yeah, good job. You see that? 2, 4, 8, 16, 32, 64, 128, 256, 512, 10, 24. So how many extra? Right, 24. So it has to be a factor of 2. In this case, the factor of 2 is really close to the number. So yeah. To create 1,000 subnets, we borrow 10 bits, and then a total of 128. Oh my God. I'll correct that. 1,024. All right. So this starts looking at the practical aspect of it, and why you might need more than one network, at least more than one. So we've got two here. There's gonna be a third one. Probably have the intranet split up into more than one network. Essentially, what we're going to be balancing out is the number of host addresses that we need to the number of subnets that we need. So we're talking about number of hosts. Remember, it's the number of addresses for that subnet minus 2. And for the number of subnets, it's just whatever the number of bits you've borrowed become the power of 2. So we borrow 1 bit, it's 2. We borrow 4 bits, it's 32. Ugh. All right, so if we need 5 subnets, and each subnet requires 40 addresses, a /26 will meet that requirement. Because, wait, there's 5 sites. Starting with a slash, oh, we started with /22. Okay, never mind, not /24. Start with this /22, we borrow 4 bits. 2 times 2 times 2 times 2. That's 16. So if we borrow 4 bits, how many total subnets are created? If you were listening, you got that. So our last question, how many total subnets are created? This is easier to do in person when I can hand you guys worksheets. I don't have a good way of doing that yet online. Almost. So I go from 22, 26. So 26 minus 22 equals 4 borrowed bits. If we have 4 borrowed bits, that's 2 times 2 times 2 times 2. It's 8. 16 subnets, actually. Must have an answer on the next one. No. Okay, BLSM is none of us has the brain power to be able to pull that off tonight. Sorry. So now, instead of having just one subnet mask size, we can have different subnet mask sizes, which is really where this style of subnetting pays off. Okay. So it looks like I lost you there. It's fine. I'll post an assignment They may ask you to do like binary to decimal, or they may suggest that in the problems. But know that this box method that I showed you works great for that. I can highly recommend this Subnet workbook, even though it deals with classful addressing. Just know that the class is defined by that first portion there. And since they don't give you, I mean, I have, so for this workbook, the answers are posted already here in the website. Oh yeah, here. Yeah. So in addition to the student one, I posted this instructor one. So if you want to see the answers to how all these things work, you can do that. They give you the classes here. So the old way of figuring out how big the network portion was to look at the first octet. And if the first octet was in this range right here, the network was a /16. If it was in this range here, it was a /24. And if it's in this class A range, it was a /8. And then the D's and E's we can't use. So if you're gonna do this, know that they use the classful ranges, but just pretend like you know, it's classless, and it's the same thing. I will only assign that one that I copied, and I'll post it. Of course, the answer's in here, and I'll give you a I'll give you one of the labs from the book too, which I saw you look at. All right, if there's no more questions, we'll call it a night. It was a good 2 hours of subnetting. Thanks for hanging in there. Hopefully this will make more sense to you guys when you get to do it. All right. Good night.